In this next section on magnetism and the study of magnetic fields is going to be section 27.2. 27.2 is a study of the magnetic force equation that is exerted on charges and currents. So if we have a magnetic field, it exerts a force. What is that force? The force is given by this equation right here. Now you've had certain forces so far. What are those forces? Well, you recall that the forces we've studied are the force of gravity, which is G m1 m2 over r squared, and is always attractive. And we've had a force electrical, and that's K q1 q2 over r squared. Very similar to the gravitational. Then we've had some other forces. The force of friction. Force of friction was some constant times the velocity, and a force of the spring constant, which is minus kx, and another force. This is a force of friction in a fluid. You can also look at a frictional force friction. That's the normal force that you have that pushes in a perpendicular direction times some constant mu called the coefficient of friction. So these are the equations we've had so far that give us our forces. Of course, force gives our mass times acceleration or change in momentum. Well, the force that we have magnetically is if we have a magnetic field, and we often use the equation, the symbol capital B for the magnetic field like we use capital E for the electric field. And if this is a magnetic field that's going along here, if we have a charge that moves along here, like an electron, might be a negative charge, or we could have a positive charge. We could have a proton. Let's imagine we have a proton that goes along here. That charge will experience a force. And what is that force? It's one of our core equations in this physics course. The force is charge times the velocity crossed the magnetic field. You remember that force is a vector. And this is to be compared to the equation that we had for the electrical force, and the electrical force was charge times the electric field. Well, this was a much simpler equation. That's why we talk about electricity first. Because if we know the electric field, then we just then we multiply by whatever the charge is and we get the force. Conversely, the electric field is the force on a unit charge, because if we divide by Q, if Q is 1, then electric field and the force are the same. This is obviously much more complicated, and we have to understand the cross product. I'm not going to give a complete review here of the cross product, but the cross product is Q, magnitude of V, magnitude of B, that's the length of the vector, times the sine of the angle between them. You recall that the dot product was the cosine of the angle. The cross product is the sine of the angle. Okay, well, how would we compute that here? Well, here, if the proton's going along and there's an angle of, say, theta right here, and this proton has a velocity v, then it will experience a force, which would be force magnetic is equal to the charge times the velocity times the magnetic field times the sine of theta. Now, let's suppose theta is equal to 20 degrees. The velocity is equal to 4 meters per second. And the magnetic field is equal to 2 teslas. Then our force would be, oh, I didn't tell you the charge here. Let's say 3 coulombs. So it would be 3 coulombs times our velocity, which is 4 meters per second, times the magnetic field, 2 teslas, times the sine of the angle, and so the angle would be the sine of 20 degrees. And that would give us our force, our magnetic force, in newtons. Well, I'll let you work that out as the student here. 3 times 4 times 2 is easy, and then you have to find the sine of 20 degrees here. And that would give us our magnitude of the force, but does not give the direction. We have to go back here and use what is called the right-hand rule to get the direction of the force. And whichever comes first, we go from the first one to the second one with our fingers in the right-hand rule. So if this is the velocity going this way and the magnetic field is going this way, the force is always perpendicular to both. That means it comes out of the paper or goes into the paper. Well, which does it do? Well, you grab that axis, like if this is the axis, you grab that axis so that you go from the velocity to the magnetic field. Well, that's obviously wrong. So we grab it this way, and this goes from the velocity to the magnetic field with our thumb pointing downward. Can't quite see that very well here, but our thumb is pointed downward, so that means that this force is directly downward. So this proton would experience a force that would push it into the paper. Force direction is into paper using the right-hand rule. The right-hand rule we've discussed previously having to do with torque. And so you have some experience with that, and if you are ambiguous about its meaning, go back and review the things that we did talking about torque and turning the water on and off with the right and the left-handed rule. Now if we use calculus, we can actually write this as an infinitesimal force. So I'm going to write this again using this equation here. An infinitesimal force, dF, is going to equal to an infinitesimal charge times the velocity, dr dt, crossed with b. And I've just re-expressed the same equation, but I've said infinitesimal force is equal to infinitesimal charge times the velocity, and the velocity is the change in the r vector over the change in time, crossed with a b. Now what I'm doing is, if you're in the course that does not require calculus, then you can just ignore this, but I'm going to use calculus to derive equations, and you're only responsible for the final result. So I'm going to take this dt and divide it into the dq, and I will get an equation then that is dq dt times dr cross b. Now dq dt, you'll recall, is the current. So this is the current I times dr cross b, or the length crossed the magnetic field b. And so we can write our infinitesimal force as the current times, and it's often written as a length, or infinitesimal length, or infinitesimal r crossed with b. And this is how a current I feels a force when it's in a magnetic field and it's a current segment dl. So let's go back now and take a small segment of current. Here's a small segment of current here. We're going to take the same magnetic field, 2 teslas. We're going to take the same angle, 20 degrees. We don't have a velocity now, but what we have is we might have, let's say, 7 amps flowing in this little wire, and this little wire has a length of, let's say, 2 meters. That's kind of a long wire, but forget that for the time being. And so what would be the force on this wire carrying 7 amps that's 2 meters long in a field of 2 teslas that's at an angle of 20 degrees with respect to the magnetic field? Again, you have to be able to solve that very simply as a current of 7 amps times the infinitesimal length. The infinitesimal length is 2 meters. Times the magnetic field, which is 2 teslas, times the sine of the angle between them, which again is 20 degrees. And I'll let you work that out, and that would give you the force. Now, what is the direction of that force? If the current, the flow of positive charge, is going in this direction, then it is that length that points in that direction crossed with the field. And so again, it'd be this vector crossed the magnetic field, and it would point downward. So the force is downward, and it will force that segment to move in the downward direction. And that explains the two methodologies that we have for looking at the force on a charge and also the force on a length of wire that carries a current. And that completes section 27.2.